Um, so we have been talking about the spectral sequence of a double complex. And today we want to specialize it to a map. And the spectral sequence is a big machinery, so it takes time to develop. There's still one thing that we need to do, and that is to give a product structure to a spectral sequence, okay? Because we often start with a double complex on which there's a product. So for example, the Czech-Duran complex, has a cup product, okay? And the product on the original complex induces a product on every term of the spectral sequence, okay? So that's what I wanted to explain now. Now, each page of the spectral sequence is the cohomology of the preceding page, okay? So if you start with a page that has a product, we want to show that the cohomology also has a product, okay? So let KD be a differential complex with a product. Oh, yes, and this differential complex, it's graded. Okay. So I write the degree n as a superscript, and I write the filtration degree p as a subscript. Okay. So this n is the degree of an element in K, and the product takes an element of degree n and an element of degree m, and it gives you an element of degree m plus n. A product is basically a bilinear map, right? And on a differential complex, you have this differential D. So we also assume that relative to the product, D is an n-type derivation. Then the cohomology has a product induced from the cup product. So if you take the class of A and you cup it with the class of B, that is defined to be the class of A cup B. Okay, yeah. Okay, so here is the definition, but we just have to show that it's well defined. In other words, it's independent of the representative. Okay. So an example of this would be the Durham complex. Okay. The Durham complex has a product given by the wedge product, and it has this property that the degrees add, and relative to the wedge product, D is an antiderivation. And you know that then on the cohomology, you also have a wedge product, okay? So it's the same kind of proof. So let Z of K be the co-cycles and B of K be the boundaries, co-boundaries. Um, so the antiderivation property ensures that one, co-cycles times a co-cycle times a co-cycle is a co-cycle. And a co-cycle coupled with the co-boundary is a co-boundary. Okay, and this is the other way. It's true too. So co-boundary cross co-cycle is also a co-boundary. Okay, so this is easy to show. We've done it for de Rham cohomology, and so so there is an induced map. Okay. Okay, so you can take Z of K times Z of K, right? And that will go to Z of K. But then you mod out by B of K. And so if you have B of K here, it is going to go to 0. Therefore, there's an induced map. You can mod out by B of K there. And B of K here times Z of K will also go to 0. And so you can also mod out by B of K. Okay? So there's an induced map in cohomology. All right? Okay. So if you start with a differential complex that has a product, and D is an antiderivation, then the cohomology also has a product, okay? Now, in the spectral sequence, right, of, say, the Czech Ram complex, you know, you start with a double complex that has a product, and then you take the cohomology, say, the first one is a little d, that's an antiderivation. So that means the first page has a product, okay? Now, then there's a theorem that says that in a spectral sequence, so each page has a product and also a differential, dr, okay? And the theorem is that that dr is an antiderivation for every r. Okay? And so this way, the product, you know, will propagate, right? So let me state the theorem. Yeah. So So suppose, so now you have a double complex. Is a double complex. Well, we don't need to say that. So suppose this double complex has a product relative to which D is an antiderivation. Okay. Then for every R, ER has okay, ER has a product. So induced from ER minus 1 and DR from ER to ER is an antiderivation. Okay, relative to the product on ER. Okay, yeah. Yeah, so well, the main thing to prove is that DR is an antiderivation. Then from the previous theorem, then you know that, the next ER will have a product, and this will propagate, right? And then for a double complex, in each degree, the filtration is always finite. So, you'll get an E infinity, and that E infinity will be just one of the ERs where R big. So E infinity will also have a product. Okay? Yeah. So if K is filtered by P in each degree, the filtration is finite. So, so yeah, so E infinity in each degree n, the filtration is finite. So E infinity n is defined. Now, if you want to multiply two elements, one of them has degree m and the other has degree n, then you just have to look at, all the elements of degree less than or equal to m plus n. So E infinity is defined, And so E infinity also has a product. E infinity inherits a product. Okay? Well, I mean, this will make more sense if we start doing calculations. Yeah. Okay. Now I'm going to delay the proof of this theorem to later, okay? Because I want to get to some calculations of examples as soon as possible. Um, yeah. Okay, so now let's apply the Leray spectral sequence to a map. The Leray spectral sequence. Okay, we apply the spectral sequence to a map, and that's called the Leray spectral sequence. Okay. So consider a C infinity map, I, from X to Y, between manifolds. And let U be an open cover of Y. Then if you take the inverse image of all the open sets, you'll get an open cover of X. So pi inverse U is defined to be pi inverse of all the open sets in the cover downstairs. Then pi inverse of U is an open cover of X. So the goal here is to calculate the cohomology of X from the cohomology of Y. And now you have an open cover of X, and now you can look at the check-theorem complex. So the check-theorem complex of this open cover for X, let's see, is let me see. So, you know, I think it's probably better that I just continue to use the same blackboard, because then you can see what I have just written. Okay, yeah. Oh, well, except, let's see, maybe, well, except I have to hide it for a while. So the check-theorem complex is CP of pi inverse U omega Q, and that is the direct product of omega Q over, you know, pi inverse of finite intersections of U. Okay. And we already know that the check-theorem complex calculates the cohomology of X. Okay, so that's what we call the generalized Mayer-Vittorus principle. The cohomology of X is isomorphic to the cohomology of the check-theorem complex. Okay, so here this dot, it means the same thing as the star. I just don't want to write too many stars. And okay, so here you have a double complex, and therefore you have a spectral sequence, and this is Leray's theorem. So under these hypotheses, since you have a double complex, and let's see, you filter it by P. So with the check-theorem complex filter by P, so there is a spectral sequence. ERDR converging to the cohomology of X. So what that means is that the E infinity term is isomorphic to the associated gradient complex of the cohomology of X. Okay? But, you know, if we are doing differential forms, then the coefficients are real numbers. Okay? We're dealing with vector spaces. So the associated gradient complex is isomorphic to the vector space itself. Right? Yeah. Okay, so for the check-theorem complex, yeah, if you turn the pages enough, so eventually you'll get the cohomology of X in each degree, all right? Yeah. Because, you know, as n goes to infinity, the number of pages you turn may go to infinity, yeah. But for each n, you just have to turn the pages finitely many times. Okay, there's nothing new there, but what the theorems does is that it identifies the E2 term, okay? So, so there is a spectral sequence converging to the cohomology of X with E2 of PQ being the Pth check cohomology of the open cover U with coefficients in the free sheaf HQ, where HQ is the pre-sheaf on X given by HQ of an open set is the cohomology of the inverse image. So we've seen this pre-sheaf before as an example of a pre-sheaf. Okay? And you noticed here that we start with, oh, sorry. No, this is not a pre-sheaf on X, right? It has to be a pre-sheaf on the space at the bottom. That's why. Because you're taking inverse image, of an open set downstairs. Okay. So you notice here that we start with an open cover upstairs. Okay. But we end with an open cover downstairs because this pre-sheaf is downstairs. Okay. So the main thing is just to identify the E2 term. And it's very easy, by what we have proven. We start with K, which is the check-Delam complex. So we have, say, CP I inverse U omega Q. And it goes up to CP I inverse U omega Q plus 1. And I mean, so this is just the direct product of omega Q over P plus 1 fold intersections. And this is omega Q plus 1 over the P plus 1 fold intersections. Okay. And the map that goes up is little d. Okay. Okay, and we know that E1 is just H little d, right? So, yeah. So E1 is H little d. Yeah. So in each column, right, you are just taking the cohomology, the de Rham cohomology of these finite intersections. Okay? So what you will get is HQ of U alpha 0 to alpha P. And then the next column would be HQ of U alpha 0 to alpha P plus 1. And okay. Okay, and what is this? Oh, no, just a minute. God. Normally, you would point out typos to me, but today I'm pointing out typos to myself because this is the inverse open cover. The open set should be pi inverse, right? Because the U's are downstairs. Eh? Yeah, yeah. So here, this should be pi inverse. Okay. And this, right? This is just CP of, now it's HQ of pi inverse of an open set. So that's the pre-sheaf script HQ of the open set. So this is CP of this open cover with coefficients in HQ. And this is CP plus 1 of the open cover downstairs with coefficients in HQ. Okay? And the horizontal map is delta. Okay? So that's the picture of H1. And then H2 is H delta HD. So E2, not H2, E2 is H delta HD. Okay. And this is precisely the check co-Chen complex of the open cover with coefficients in the pre-sheaf script HQ. And so therefore you're just gonna get the check cohomology of the open cover U with coefficients in HQ. Okay? So that would be the general term. And the next one would be the check cohomology HP plus 1 of U HQ. And right, so that's what the theorem says, right? So the theorem says that's HQ. That's E2 PQ. Yeah. So so now the problem is to figure out what that is. Okay. Once you know E2, then you can compute E3, E4, and so on, in order to get E infinity, and then E infinity will give you the homology upstairs. Okay. Okay. So this is for any map, okay? And we're going to apply it to a fiber bundle. And yeah, so for a fiber bundle, okay, it specializes to something computable. Yeah. And this is the theorem. Okay. So theorem. Yeah. So let pi going from E to M be a C infinity fiber bundle with fiber F. So in Leray's theorem, okay, so in the Leray spectral sequence, if M is simply connected, and the cohomology of the fiber is finite dimensional, okay, then that E2 term can be identified with the tensor product. Oh, and yes, and U is a good cover. M is simply connected. This is finite dimensional, and U is a good cover of M. Then you can identify E2 with HP of the base tensor with HQ of the fiber. Okay? And so if you calculate the spectral sequence by turning the pages, eventually you get the cohomology of the space upstairs. So that is the manifold E. Okay? Okay. So when you have a fiber bundle, you have three manifolds. You have E, M, and then the fiber F. Okay? And so the spectral sequence relates the cohomology of these three manifolds. So sometimes if you know the cohomology of M and F, you can determine the cohomology of E, okay? And sometimes it can work the other way. So if you know the cohomology of E and F, you can determine the cohomology of M, okay? So I will do an example. It will calculate the cohomology of CP2 using the Leray spectral sequence. And yeah, so I'm going to leave the proof to later because I would like to do an example after the break. Okay, so. Okay, so let's take a break now. And then after the break, we'll apply this to calculate the cohomology of CP2. Now, there are various ways to define CPN. You can define it as, the set of all complex lines in a complex vector space. So you define an equivalence relation on a complex vector space and take the quotient just like in the real case. But there's another definition using spheres that is better. in topology. Okay? So in algebraic geometry, usually you want to define it as a quotient of a vector space, without the origin, because spheres, are not algebraic varieties over the complex numbers. But in topology, it's easier to work with spheres. So I'm going to define CP2 this way. So you look at points, okay, say in C3, and you look at the unisphere, okay, in C3. So each of these Zj, okay, is Xj plus Yj, the square root of -1, right? I don't want to write I, because we often use I for subscripts. So the unisphere in C3 is defined by the sum of the norms being, the sum of the norm squared being 1, and this would be x0 squared plus y0 squared plus x1 squared plus y1 squared plus x2 squared plus y2 squared equals 1. And so you see that it is just the unisphere in R6, okay? So the unisphere in R6 is S5. This is S5. And then we define an equivalence relation on S5. Okay, so yeah, so it's basically elements of it's vectors of norm 1, right, in C3. So we define an equivalence relation on S5 by, okay? So these are vectors of norm 1. Therefore, if you multiply by a complex number of norm 1, you'll get another, vector of norm 1. Okay, so we say two vectors are equivalent, okay, if one is a multiple of the other by a complex number of norm 1. Okay, so a complex number of norm 1, that's in the unisphere, okay, of C star, okay? So C star, that's C minus 0. Yeah. You have to use complex numbers of norm 1 in order to keep the vectors both of norm 1. So you define this equivalence relation, and then CP2 is defined to be the quotient. It's defined to be S5 quotient out by this equivalence relation. Okay? And so there is a map from S5 to CP2, the projection map I from S5 to CP2. And it's not difficult to show that this projection map is a fiber bundle. So in other words, it's locally trivial. Okay, locally is a product of an open set here with a fiber. Now, a fiber is just elements, vectors that are equivalent. Therefore, all the vectors equivalent to a given vector, they are multiplied by an element of the sphere. So this is a fiber bundle with fiber S1. Okay? Yeah. So we usually write the fiber bundle with fiber S1 like this. You have a fiber bundle with fiber S1. Okay? Okay, now we know the cohomology of S5. We know the cohomology of S1. Okay? And now we want to calculate the cohomology of CP2, okay? Using the Leray spectral sequence. Yeah. Okay, and oh God. Now, CP2 is simply connected. Mhm. It's very easy to prove if you know, if you have studied the homotopy exact sequence of a fiber bundle. Okay? So when you have a fiber bundle, then there's an exact sequence relating the homotopy groups of these three spaces. And because these two, oh, okay, this is not simply connected, but yeah, from that homotopy exact sequence, you can prove that CP2 is simply connected. I think, for now, we'll assume that because that's going to take us into topology that's not quite relevant here. So all the CPNs are simply connected, okay? So let's assume that as a fact. All CP. I haven't defined CPN, but you can see how to generalize the definition. All CPNs are simply connected. Okay? And so that we can apply Leray's theorem. Yeah, so certainly M is simply connected, F is finite dimensional. And then, you know what, like, we don't really need this term, right? Yeah. We only want to know what E2 is. So I think in the theorem, I shouldn't even mention this. And then I don't have to make any assumption on any open cover. There's no open cover in the theorem. Yeah? So E2 is simply the tensor product. Yeah, so let's write down E2. Okay, so it's HP. Now this is P, okay, and this is Q. Okay. So now when Q is 0, right, you have H0 of F, and that's just R. Let's see. I need a little bit more space. So yeah. H0 of F, that's H0 of S1. S1 is the fiber. That's R. Yeah. So E2, E0 is HE of CP2 tensor with H0 of S1, and that's HP of CP2 tensor with R. So remember, we have a lemma. When you tensor with R, you get the original space, HP of CP2. Okay? So what that says is that in the 0th row, you just have the cohomology of CP2. And then, so similarly, in the 0th column, right, you have H0 CP2 tensor with HQ of S1. Okay, now CP2 is connected. So why is that? Why is CP2 connected? I mean, it is, right? Pardon? Yeah, right, because like it's the image of S5, and this is a surjective map. Right? Yeah, this is a surjective map because CP2 is defined to be the quotient of S5, you know. So this is connected because it's the continuous image of a connected set. Continuous image of S5, which is connected. Okay? And because it's connected, H0 is R. Okay? And so this is HQ of S1. Okay, so that says that the first column is just the cohomology of S1. This column is the cohomology of S1, and you know what it is. In H0, it's R, it's generated by 1, right? It's constant functions. Okay, I'm just writing down the generator. H1 of S1 is R, and it's generated by some one form, but I'll call that X. And then it's all zeros. Okay? So E2 looks like that so far. And now let's look at D2, the differential. So D2 goes down by 1 and across by 2. Yeah. You see, like all the D2s will be 0 except for this one, right? This D2, this one may or may not be 0. Oh, yeah, right, because like all the others, now E2 is a tensor product. So, you know, if one term is 0, then the whole thing will be 0. You know, you're taking the tensor product of this column, the 0th column with the 0th row. So what do I put in here? Here. What goes in this box? I mean, this Okay, this box is E2 of 1, 2, right? So I need some space. Okay, so let's see. So let's look at this box, E2 of 1, 2. Okay, that is H1 of CP2 tensor with H2 of S1. But H2 of S1 is 0. So this is going to be 0. Okay. Okay. So this box, yeah, E2 of 1, 2, this is 0. What is this box? Same thing, 0. It's just tensor with 0. These are all 0. And then up there, it's all 0. Oh, yeah. So, okay, yeah, so D2 could be non-zero because you don't know what these things are. You don't know what these boxes are. Okay, yeah, D2 could be non-zero. But what about D3? What can you say about D3? D3 has to go down 2. Always 0 because these 2 rows are the only 2 possible non-zero rows. But if you go down 2, you'll go into the negative region, okay? So, so we know that D3 will be 0. D4 will be even more 0 because it goes down 3, okay? So D3, D4, D5, and so on. They're all 0 because they, well, either they go into the negative region or they are coming from these zeros. Yeah? You have only 2 possible non-zero rows, so they go into the negative Q region from rows 1 and 2. Right? And okay, so if D3 is 0, well, what can you say about E4? E4 is the cohomology of E3, right? But D3 is 0. If the differential is 0, then the cohomology is the same as the original complex. Okay, so E3 equals E4 equals E5 equals E infinity. Okay? And E infinity, E infinity is supposed to be the cohomology of the total space, right, in the spectral sequence. In the Leray spectral sequence, E infinity is the cohomology upstairs. So E infinity is the cohomology of, we have this fiber bundle where the upstairs is S5, E infinity is S5. Right? And we know what that is. Okay, so let's draw a picture of E infinity. Well, E infinity is the same as E3. and it's the cohomology of S5. Okay, in the spectral sequence, once it's zero, it's always zero. Right? You're taking cohomology of zero, and that will always be zero. Okay, so E infinity can have only these two non-zero rows, and it's going to be the cohomology of S5. Which of these boxes can you fill in? S5 is non-zero in only 2 degrees, right? So what would be this box? What's this box? It has degree 1, and it's supposed to be the cohomology of S5. So this has to be 0 because S5 has nothing in degree 1. Okay? So this is 0. What about here? 0, because this is degree 2. Okay, this is 0. How about here? 0, that's degree 3, right? And this is also degree 3, nothing. Here, 0. Here, 0, degree 4. Okay, and now degree 5. Degree 5 is R, so it's got one generator. So it has to go into one of these boxes. Which box does it go into? Somebody said this. So this one. Okay, why not here? Oh yeah, like here, what's in this box? Remember, this row is HP of CP2, right? The bottom row is the cohomology of CP2. So what's in this box? 0, and why is it 0 here? Yeah, because CP2 has dimension 4. Okay? It's S5 mod out by S1. So this has dimension 4. Real dimension 4. And so it doesn't have any cohomology in degree 5 or 6. So actually, you only have these few boxes that can be non-zero, okay? And like once it's 0 in E2, it has to be 0 forever. So because you were just taking cohomology of this box to get the next box, okay? So this has to be 0. In fact, we know that all of these are 0. Yeah, so H5 of S5 has to go into this box, okay? So so there is something there that, and I'll call the generator Z, and then obviously here, that's H0, so it's generated by the constant function 1, okay? So that's what E3 looks like, okay? Yeah. So our goal now is to fill in these boxes. Once we fill them in, then we know the cohomology of CP2, okay? Yeah, so let's look at this box. Okay. This box, okay. Now D2 is going to go down 1 and across 2. So D2 will go here, okay. And it will go to 0. Okay. And then there's a D2 that goes in here. Let's see, it will be coming from here. So the D2 that comes in and out of this box are both 0. Okay, so let's write that down. Okay, so now we are looking at this box is E10. So it's E2. E210. It has a D2 that goes out, and it has a D2 that comes in. And then, yeah. Yes, and so let's see, and E3 of 1, 2, okay? That's the cohomology of this complex. Oh yeah, but the D2 is all 0, so so the cohomology will be itself. Okay? Yeah. Right? Because E3 of 1, 0, yeah, that is, that's the kernel of D2, this D2, in degree 1, 0 over the image of D2. So it's the stuff that goes into this box. And okay, yeah, the kernel of D2 is E210. The image of this D2 is 0, so it's E210. Okay? Yeah. So E310 is equal to E210. And we know that E310 is 0. So this box has to be 0. Okay? And once you know that this is 0, what is this? What's this? Remember E2. E2 is the tensor product of the bottom row and the 0th column. So if this is 0, this is 0. Okay? You're taking the tensor product of this with 0. Okay? And now let's look at this box. So again, the D2 that comes out, it goes to 0. But let me see, where does this box comes from this box, right? Yeah, down 1 across 2. And so that's also 0. Okay? 0 in, 0 out. So for the same reason, this will be 0. And this will be 0. Okay? And yeah, right. So now we have to look at this box. This is E2 of 2, 0. And it comes from E2 of 0, 1. Okay? Okay. So consider E2 of 0, 1 goes to E2 of 2, 0. Okay, and there's a D2 here that goes to 0. And then there's a D2 that comes in here, comes from 0. So you have this sequence. Okay? But we don't know if it's exact or not. Okay. But if you take the cohomology of this sequence, what you get is E3, right? So cohomology of this sequence is E3, 0, 1. It's this. But E3 is right there. What is E3 of 0, 1? E3 of 0, 1 is this. It's 0. Okay? And E3 of 2, 0 is this box, and that's 0. Okay? So the cohomology of this sequence is 0. What does that say about that sequence? When the cohomology is 0, what can you say about the sequence? It's exact, right? It means the kernel at any term is the image, because that's the cohomology. So it said that the cohomology is 0. That means the kernel is equal to the image at any term. So therefore, this sequence is exact. And if this sequence is exact, that means you have an isomorphism. So this is an isomorphism. Okay? Yeah. Okay. So this is an isomorphism. And that means, what is this box? It has to be R, and it has a generator. So we call that generator U. Okay? So hence, E220, that's H2 of CP2 is R, okay, with generator that we just call that generator U, okay? And then here you have the tensor product. So this will be R because it's R tensor R, so it's R, and its generator will be X tensor U. Okay? And then, and the same argument, exactly the same argument will say that this is also an isomorphism. Okay? And okay, now instead of writing that, we'll just write XU, okay? Just to be simpler. And so this D2 is also an isomorphism. And, okay, so this U is D2 of X. Okay. And now let's calculate D2 of XU. So d2 of xu, that means x tensor u. So you have an anti-derivation, so it's d2x u plus x has degree 1, so it's minus 1 x d2u. Yeah, and d2x is u. So you get u times u, and then d2u is 0, u square. Okay, so that's the generator here. This box has u square. And then this box would be R with generator ux square. Okay? And now you have the cohomology of CP2. Okay? So therefore, the cohomology of CP2, it's it's R with generator 1, and then R with generator U, and then R with generator U square. Okay? So you can write that as the polynomial ring R of U, and then you quotient out by U cube. Okay? So that means you set U cube equal to 0. Okay? And so you see that not only do we have the cohomology of CP2 as a vector space, we also have the cohomology as a ring. You know, this gives you the ring structure, right? Because you know how the elements in the cohomology multiply. They are just multiples of U. Okay? Yeah. So this is the cohomology ring. CP2. So in the homework, I ask you to calculate the cohomology ring of CPN. And it's more or less the same calculation. You just have to go further. Okay, so I'm going to stop here today. Now,